Welcome to Programming in Modern C++. We are in week 10 and I am now going to discuss module 50. In the last module, we discussed the differences between copying and moving and understood the difference between Lvalue and Rvalue. We observed that C++ 11 from version onwards is taking the advantage of move using Rvalue reference and defining the move semantics in terms of move constructor and assignment operator. So, this particular feature does not give us anything specific in terms of modeling better or giving more capability of expression, but if it is a very important performance feature. We will see the modeling, there are modeling consequences as well, but primarily this is for performance. Now, while we have seen the basics, now we need to learn to implement the move semantics in any class that we define. So, we are going to take a look at the challenges and how to work around them using a library function called std::move. We will also learn how std::move is implemented and then put all these things together to complete the jigsaw puzzle through a move enabled UDT project. So, this is the outline which will be on the left. Just to specifically quickly recap the copy versus move and related concepts that we did in the last module, because we will heavily use them in this. Recall that C++ has supported copying of object states through copy constructor and copy assignment operator, whereas C++ 11 adds the support to request moving objects for performance improvement. And we have seen several examples for that improvement that can happen when you return a value from a function by return by value mechanism, when you append to a full vector or you swap two variables, or different contexts where there is a choice between shallow copy and deep copy. So, C++ 11 adds the related optimization through Rvalue reference and move semantics through move constructor and move assignment operator. So, what is the difference between Lvalue and Rvalue that we have learnt? Lvalue is generally which has a name, that is where we can take the address of. If we can take the address of something, then it is an Lvalue. If we cannot take the address of, then it is an Rvalue. In C connotation, these names came from the fact that anything which is on the left hand side of an assignment has to be an Lvalue, and anything on the right hand side may be an Rvalue. But the C++ semantics have moved from that. So, it is better to think about Lvalues more as locator values, which locates something. So, Lvalues will be named objects, typically variables, and you can apply the address of operator and they have their usual Lvalue reference. Rvalues in contrast are unnamed temporary objects like expressions returned by value from functions, etc., literals of different programming of different data types and so on. And we have introduced an Rvalue reference with 2 ampersand following that type, which identify objects that may be moved from, need not be copied necessarily. So, this introduces possibility of important overloading and their resolution between Rvalue and Lvalue references. Note these last 4 points and try to understand and keep them in your mind always, that Lvalue may bind to Lvalue reference. right. You can, that is what we had so far. Rvalues can bind to only L-value reference to constant. This also we had seen that if we had to define a reference to an expression, we had to define that as a constant reference. So, L-value reference to constant, R-values can bind to. R-values naturally may bind to R-value references to non-constant. They can bind to R-value references to constant as well, but that does not have much meaning as of now, as we had mentioned earlier. And finally, L-values may not bind to R-value references. You cannot use an L-value in an R-value reference context, because R-values are not supposed to have a name or supposed to. So, if you do that, then you lose the name of the L-value, lose the ability to take its address and so on, right. So, this is with this quick recap, let us dive directly into the problem of how do we code for the move semantics. So, basically we have two tools at hand. In a class we had copy constructor and copy assignment operator, that was to copy object states. Now, in addition we will have a move constructor. It looks exactly like the copy constructor except for this added ampersand, which says that this is a constructor which takes an R-value reference. Similarly, the move assignment operator, which looks again like the copy assignment operator, except that it takes a R-value reference as a parameter. So, when you do a move, what you want is two things. One is you move the source's value into your current value, right. You do not copy it, you just move that value, and with that you may change the value of the source, but if you change, you still have to leave the source in a valid state. So, with this you will see one major difference with the corresponding copy functions. For example, when we write a copy constructor, usually we will write a const here, because we do not want, or here in copy assignment we will write a const, because we do not want the source to change. But here I am moving from the source, so I necessarily need the source to change, therefore, const will not be applicable in this context. So, if MyResource class has a resource like a character pointer which is initialized to null, such initializations are allowed in C++11, we will see that more. So, in the copy constructor, I am copying from the R-value reference RR. So, the resource is rr.str, I just move it here. So, I expect that. So, if you think in terms of cat start, so this is just a pointer assignment, right. So, what will this mean? That this current object's str and RR's str both will point to the. So, there is this array of characters where RR, the R value reference was pointing to, and now you have this object and you are referring to that, right. So, then what you do to complete the move, you change the state of RR by doing this, that is you break this and you ground this. So, what you have done, you have moved the value from the source and you have actually nulled the source. So, you have changed the source, but it still is in a valid state, I mean it is not a dangling pointer or things like that. So, that is precisely the basic idea of doing the move semantics. Now, if you have to do an assignment operator, then what you will have to do, you already have in your current object you have an str. So, you have to release that resource, because after move naturally that will not be there, and then again you do a move from the source, which is in this case is a pointer assignment, right. So, again two objects are now pointing to the same resource, and therefore, you change the state of the source by setting it to null as you did before. So, the pointer has moved to your custody completely, and then you return this. So, this is the part which you would not have done in case of a copy constructor, and rest in case of at least the built-in types or PODs, as we say, plain old data types, will be sim. So, this is the basic idea of doing a move. Now, naturally, if you do that, then there is a consequent question of what happens if you have a move to self, like we had seen the copy to self problems. So, that will certainly be a problem, and the same solution, the same guard solution will work, that if you find out the address of the current object and the address of the source object are same, that is, they are same objects, then you do not do the move like you did not do the copy. So, that is a simple fix. Now, let us look at what if the resource that we are using is not simply a pointer or not simply a plain old data type, but it is a user defined class. So, the resource class that we just saw, I am writing another my class which has a resource of MyResource type, and we know that MyResource is move enabled. It has a move constructor, it has a move assignment operator. Besides that, constructor, default constructor, parameterized constructor, copy assignment operator, destructor, all of those will be there. That is a routine part, but move is the part that we are focusing on. So, we have that kind of a move enabled one. So, with that, I try to, in a similar way, try to write a move constructor and a move assignment operator. Now, in the move constructor, naturally, I will have to take from the resource. Similarly, in a move assignment operator, I have to make an assignment of the resource from the source, right? Same thing I have to do. Now, what is my expectation is, since my resource is of move enabled type, that it has a move construction, move assignment. So, when I try to do this, this is basically a construction of MRRC in my class object. So, I will expect that the copying will not be done, it will be done by a move construction. Similarly, here when I do the assignment, this is an assignment in the MyResource class. So, I will expect that there will be a move assignment that will happen. Well, if you do this, you will find that actually that is not happening. The copy is actually using this, that is, what is this? This is a copy constructor, not the move constructor. This is the copy assignment operator, not the move assignment operator. It is compiling. You have enabled MyResource class, but it is still not doing that. The reason is why? Very simple. What you have given to this as a parameter is a named object. Therefore, c.mrc is a named object. It has a address. Therefore, it is an L value, and as you give it an L value, that matches with this overload, not with the move versions of the constructor and the assignment operator, right. So, this is not going to work. So, that is the pitfall that you get into, that for POD you could do that easily, but for UDT it is not working. So, that leads to the problem, and this is another illustration of the problem in the other context, that if you have a hierarchy. So, you have a my base class, so which has copy constructor as well as move constructor. Similarly, assignment operators will be similar, and my class is basically a specialization of that. So, in the my class constructor, my class move constructor, I will need to move the base class part of the source object. Source object is C. So, I would expect that I will be able to move that, that is, this should call this move constructor of my class base, but the unfortunate part is it does not, it calls the copy constructor part, copy constructor function of the my class base. The reason is again the same, C is an L value, right. So, if we try to summarize this problem, so we are not being able to do this for the UDTs. So, if we look at it in general terms, so naturally in an UDT you have two kinds of constituent objects. One is the data member objects, and the other is, if it is on a hierarchy, which is the general case, you will have a base class part, right. So, you have a, so these are the two examples that we have seen, the data member and the base class part. Now, when you are trying to do move or copy in the construction or through assignment operator, then the move and construction of the underlying class has to be called, whether it is MyResource class or my class base class and so on. So, the construction, so these are the construction and assignment expressions that we have seen. So, for copy we will use the copy and assignment operators, copy constructor, assignment operator. For move we need the move construction and move assignment operators to happen, but in all these cases we have named resource, which is an L value. But to be able to invoke the overloaded move constructor or the overloaded move assignment operator, I need an R value for that matching, right. So, I need a mechanism in general to convert an L value to an R value. Only then I will be able to do this, and std : move is an utility which precisely does that. So, let us discuss std : what std : move does. So, what I do, fix is very simple. Std : move is given in this component of standard library. You include that, or actually it is in turn included in several libraries. So, you may not explicitly need to include that. So, all that you need to do is simply the parameter you first pass to std : move. So, you are passing an L value here, and what std : move guarantees you that it returns you the same thing, same object as an R value. Similar thing you do here. So, this is for the base class type, this is for the data member type. Similarly, in assignment also you do the same thing. So, all that you need to do is use std : move function as a wrapper to convert the L value to the R value, and that would solve the entire problem. So, what does that do? What does it actually do? So, what it does is simply, for example, we can see it like this, that suppose I want to permit move from say star begin, the iterator star begin to temp. Now, the way I can do is use this kind of a typecasting, which basically says that star begin is an L value, and you want to set the value type to an R value. You can do this by a static cast, by a C style cast, but certainly you will have to write so much for doing that. Not possible to remember. You can just do std : move, and that does your job, right. So, that is the whole issue that we are dealing with. Now, before we understand how does std : move work, we need to understand the concept of reference collapsing in template, right. So, std : move is a template, obviously, because it is working for any type. So, in C++ 03, if you see, and if you had a template like this, type name T and you have T ampersand, and then you are trying to pass a value x to this function f, then naturally x goes, x's type is int ampersand, because it is a variable, it is an L value. So, its type is int ampersand, right. Now, the point is, so this will deduce, if you do this, this will deduce that T is int ampersand. So, what happens in the body of the function? The T, actually what you are calling f as is int ampersand, which you have resolved T to be, and then the ampersand that already exists. So, you will have T int ampersand ampersand, of course, not together, not the R value reference, that concept was not there. So, C++ 03 has a simple rule that if a reference is applied to a reference, then it becomes a single reference. So, T ampersand ampersand is T ampersand. In C++ 11, now you can get different combinations. What if here I pass int ampersand ampersand? what will be the resultant type? Is it an Rvalue reference or an Lvalue reference? So, these 4 rules are the possibilities, right. So, if this is the old rule that Lvalue references collapse. In terms of Rvalue reference to Lvalue, Lvalue reference to Rvalue, both collapse to Lvalue. Only Rvalue reference to Rvalue reference collapses to Rvalue reference. So, the rules finally turn out to be very simple. First 3 rules say that if any of the references is an Lvalue reference, then the resultant reference is an Lvalue reference. Otherwise, if both are Rvalue reference, then it is an Rvalue reference. So, you try to make use of that, and let us see what will be std move. So, it is a function. So, I need to decide the return type, I need to decide the parameter type, and obviously, I do not want the object to change. So, the object that goes in has to come out, that is the simple thing. So, for return type, what do I know? I need to, what I need is that the return type has to be Lvalue reference, but what is gone in may be a Lvalue reference, may be an Rvalue reference, I do not know what has gone in. So, I do something very simple using another library function called std : remove reference applied to type t. So, what it does is tells the compiler that if t has a reference, remove it, whatever, right, and then make a type which is a Rvalue reference, right, done. So, the return type is solved. So, this is the return type of the move function. I pass move, I pass the object, return the object. So, what I get is an Rvalue reference object, it's simple. The question is, what is that I write here, right? And we will see that how does that impact the final thing. So, we have addressed the return type of std : move. What will be the parameter type? So, parameter type, what are the things that we know? That it must be a non-constant reference, because we want to move its value, right. So, that is clear that it has to be non-constant. First point is obvious. An Lvalue reference will not work because Rvalues cannot bind to them, very simple, right. If I write like this a function and then I write std : move with a Lvalue reference as a parameter, then obviously a call like this will fail, right, because Lvalue reference cannot be converted to an Rvalue reference, we know. Can it be an Rvalue reference? If it is an Rvalue reference, then the first question is, why are we actually calling this, calling the std : move, and in any case an Rvalue reference cannot bind to an Lvalue reference. So, if I have this as an Rvalue reference and try to pass an Lvalue, which is an object Vt, then this will be an error, right. So, the requirement turns out to be very simple, that for Lvalue arguments I need a parameter type which is Lvalue reference. For a Rvalue argument, I need a parameter type which is Rvalue reference, right. So, it smells of that std : move itself is smelling of an overloading, right. So, let us try to overload. So, I can have 2 versions of the move, one that is a Lvalue reference and one that is an Rvalue reference. This will solve the problem, because if I pass an Lvalue, this will be called, and I will just remove the reference and put the Rvalue reference type onto that and give it back as I wanted. If the passed parameter is Rvalue reference, then the other overload will work. Unfortunately, I mean, in this situation it looks like it will work, but unfortunately there is this solution will not work for the perfect forwarding problem. We still have not studied perfect forwarding problem. We will do that in a later module. Perfect forwarding, the basic idea is simple, that if I have a template function which in turn is passing the parameter, the template parameter, to another function, that it is forwarding the parameter to a function, which will be very common, a function calling a function, and all in the template environment. So, a templatized function got a parameter, it is passing that parameter to another templatized function. If we have to do that, then depending on how many parameters I forward, I will have all possible combinations of L values and R value, L value references and R value references. For example, if there are two parameters, both can be L value. If there is one, if the first is L value, second can be R value reference. If the first is R value reference, second could be L value reference, both could be R value reference. So, I will need 4 such overloads. So, if I have n parameters, n arguments, I will have 2 to the power n overloads, the problem explodes. So, this solution is not going to work. So, what we make use of is the interpretation of R value reference in the template. So, let us see what happens. Suppose I have a template function where f, where the parameter is a R value reference. Right? Now, what will this happen? This will, the t will be deduced depending on what is passed to it. Right? For example, if I have L value, then t ampersand ampersand. Now, if I have passed an L value int ampersand, then what will happen? Reference collapsing, an L value and an R value. So, it will get collapsed to the L value reference. If I pass this as a R value, then it as it is matching, is a non-reference, right. So, this is something very, very interesting, that because of the reference collapsing rule, the R value reference in a template could kind of automatically act as a switch. Just to try this code out yourself. Say I have an int x, I have this function f with R value reference. If I call f x, you will find that I am trying to set t as int ampersand. So, it calls the function as f int ampersand. If I pass 10, 10 is a literal. So, it is an R value, it calls f with int, which is int ampersand ampersand, right. In contrast, if I have a vector v t and I call f with that, I am passing an L value. So, it will naturally call t vec ampersand because of reference collapsing. If I have a function like create v t which returns a t vec, it is an R value. If I pass it, it will call as a. So, I can see that there is something magical about this particular reference type as a parameter in a template, where because of reference collapsing, I can, depending on the type of reference I pass, it automatically works. Right? So, I have partly solved another part of the problem. This was the return type I had already, and this is the parameter type that I have decided on. But still there is a problem. What is the problem? The problem is you are returning obj, it is a named object. So, it is an L value. So, move's return type is R value reference, but this is an L value. So, this needs that the L value needs to be binding to an R value reference. The L value reference has to bind to an R value reference, which is not allowed, as you know, because that will make the whole thing break down. Fix of that is very simple, just do a cast. So, what you do is you just static cast to the return type. This is a return type, right. So, you just do a static cast of this object to the return type using that remove reference function, and as you do that, you have now an R value which you can easily bind to the R value reference, and that is the final. So, you can see that it needed some explanation of the mechanism that goes behind std::move to understand, but this is exactly what the std::move function looks like, which is a 5-line function which enables you to do implement the move semantics in a very, very beautiful way. So, here I have just summarized the beauty of T ampersand ampersand or reference R value reference parameter in a template to so that you can remember it. The main point to take back is that if it gets an L value argument, it treats it as an L value reference. If it gets a R value argument, then it treats it as an R value reference. So, it kind of does a swap in any way. Right. So, we will talk about this lot more in a later module when we talk about universal references. Now, before I close, here is a simple project that I created for you. I will not go through these slides because these are primarily code for you to understand. But what I wanted to put together is we have talked about move enabled classes for having PODs as resource. We have talked about move enabled classes with UDTs as resource and how to put them together. So, here I have given a project where there are 3 class. MyResource we have already talked of. My class MyResource has a cat star, a POD resource. My class has MyResource data member. So, it has a UDT resource, and in addition I have given a class here resource manager, whose purpose is to track the resources. So, what I do is when I need a POD resource, because that is the bottom line where the actual allocation will happen. If I need a POD resource, I will need to do a malloc or free or a new or delete. So, instead of doing that, I provide 2 functions in this resource manager, a function to create and a function to release. Right. So, as those functions get called, you can easily track how many objects have been created and how many objects have been released. Right. And then there is a stat function to print that information. You could do that by overloading new and delete also, but I just did not want to complicate things. So, with that I show the both versions of copy only version of each class, my resource and my class, and copy and move version of these classes, and we for the same application we evaluate how many resources are created and how many resources are released to get that even in a simple application what kind of benefit that you can get by the realization of the move semantics. So, this is your resource. I mean you go through the details, it is heavily commented. So, you should have no problem in understanding this. So, this has 3 static methods, static because I just want to call it from anywhere without tracking the object, and actually this should be ideally this should be designed as a singleton class, which I did not do. You can do that. And since this has 2 data members which keep on counting, these are counters of how many have been created and how many have been released. And the resource manager is instantiated outside of main in the static global, so that it gets created before main starts and it will get destroyed after main ends. So, anything that happens within the main in terms of creation and release will get tracked to this call to these functions. So, my resource POD class is and further for every function there is a name that I have used inside to basically tell you, so that we can track that which function is getting called. So, CTOR R is the constructor for resource class, CTOR R is copy constructor for resource class, C assignment is copy assignment for resource class, and so on and so forth. So, this is a copy only version, and if you look into that, there are couple of things that we are doing. We are constructing a resource object by parameterized construction, we are doing a copy construction, we are passing it to a function which simply returns that same object. So, kind of a move that does not do the move semantics, it just takes the object and copies it, call by value, return by value. What happens if you do that? Copy assignment, default construction, the same copy assignment with the function call, and you can see in the comments as to what traces you get and how does they work. And in every case, for example, one case I might just talk about, say in this, you see there is a copy constructor of resource. Why? Because the function f is being called on a call by value. So, a copy construction is required, and you will see a destructor for that. So, this is for passing the parameter, and once this is called, then function f is called, and then you have a copy constructor to actually construct R3 from this value. So, it is of that kind. In some cases of assignment, this is little longish. So, you should try to trace them through the debugger, and you will see that. With this, we get 8 resources, the POD resources, 8 resources created and 8 resources released. Then we provide the version which has the move constructor and the move assignment. We have just seen how to do that. That is what I started with, and the same application is then written in terms of the copy and move MyResource, and you can see that the resource creation and deletion has dropped from 8 to 5. So, 3 less resources, since we are making use of move in the same context. The application is identical. Then I move on to the my class, and first provide the first solution that we had seen earlier, which you know is broken, because even though it is a move constructor or a move assignment operator, it will actually call the copy versions of the MyResource class. So, with that, this kind of turns out to be copy only, though it was meant to do move and copy both. And then there is an application which in a similar way tries to do different things of copy and move. 7 resources dealt with. Next, we fix this by using using the std : move we have just learnt, and with that then we rerun. So, now we know that move and copy will get dispatched in the proper way, and then we find that the resource usage has dropped for exactly the identical application, has dropped from 7 to 4, right. So, again 3 benefit, I mean it is close to 40% benefit that you are getting. In some cases you may get less, in some cases you may get lot more. Now, treat this whole project as a single code. We can just put it all together, run it, get debug through it, and get convinced as to how things are happening. This will be an excellent resource for you to develop any move enabled classes in future that you might need to do. Everything that you require are given in this small project. So, to summarize, we have learned to implement the move semantics in UDTs using std : move. We have understood the implementation of std : move, and also have given a simple project. Thank you very much for your attention, and we will meet in the next module next week.